So today what we're going to be doing is we're going to be graphing quadratics in Vertex form. Now, this is going to be very similar to how we've graphed absolute value functions in the past. So we've put down a repetition of the rules that we discovered when we were graphing absolute value. Left and right are adding or subtracting inside the parentheses. So if we ever have any parentheses, it's going to be what's inside. That's a left or right motion. Nothing there. That's a left or right motion. Adding or subtracting outside the parentheses is going to be an up or down motion, which is what we're going to see with something like this. Outside the parentheses, that's going to be up or down. Stretching and compressing. Now, we talked about with absolute value, the slope to the right. Now, stretching or compressing is going to be that same concept, but with a quadratic, because it's a curve, the slope is going to operate a little differently. But we're going to see what happens when we have things like multiplied outside. These are both going to be stretched. These are both going to be compressed. Likewise, if that was a 2x line, that line goes from a diagonal to a much steeper diagonal. That's thought of as stretching the line. If this were a diagonal, that 1/2 means that its run is going to be longer. We can think of that as compressing the line. So those are stretching and compressing. And then the last that we're going to be doing is we're going to be flipping it, changing the sign on the outside like this. All that does is it turns the graph upside down. So let's go ahead and let's get started on a few of these. Now with this is our parent graph of a quadratic function. So we're going to build ourselves a table just to see what the parent graph looks like. So if I have, let's pick some values. Let's say -2 to 2. Just to see where we get. And now if we plug these values in, I'm going to say, okay, so -2 squared, -1 squared, 0 squared, 1 squared, and 2 squared. That's going to give me 4, 1, 0, 1, and 4. And this is going to be the general shape of our parent function. So what I'm going to do is I'm going to graph 0, 0, -1, 1, -2, 4, 1, 1, 2, 4. And we see that it kind of makes something like a V, but in this case, it's not a complete V. It's actually a curve. And this curve we call a parabola, because it's very, very steep, and as it gets closer to the vertex, it starts to flatten out until at this point, we're dealing with a completely flat line. Then it bends back up on itself. So that is the parent function. So y equals x squared. There we go. So we're going to be distorting this graph by moving it left and right, up and down, stretching or compressing it, or flipping it. So let's see what happens to our first set. So what we recognize in here is that this -1 inside the parentheses is going to mean adding, subtracting inside is a left or right motion. Because we are subtracting 1, that means we are moving to the right. So I'm going to go ahead and I'm going to graph my parent function with the points that we just graphed, and we're going to move it. So this is my parent. And what we're going to do is we're going to move each one of these points to the right by 1. So I'm going to move this point to the right. This point is moved to the right. My vertex, that point, and that point. So we have a new parabola that, as we can see, has been shifted slightly to the right of where we were before. And this is my y equals x minus 1 squared. Now, some of you might say, well, that's all well and dandy, but I want to check to see, can I actually do that? And we can. If we were to actually build an xy table, we would come up with these points. So you can either plug in these values, or I'm going to plug in my new x values and see if I end up with those 5. So it looks like I have a value at -1, 0, 1, 2, and 3. And I'm going to plug all these in to this right here. So negative 1 minus 1 squared, 0 minus 1 squared, 1 minus 1 squared, 2 minus 1 squared, and 3 minus 1 squared. We know that negative 1 minus 1 is negative 2. Negative 2 squared is 4. 0 minus 1 is negative 1. Negative 1 squared is 1. 1 minus 1 is 0. 0 times 0 is 0. 2 minus 1 is 1. 1 squared is 1. 3 minus 1 is 2. 2 squared is 4. So let's see if these points coordinate with our new red graph. And so I have negative 1, comma 4. That point checks out. 0, comma 1. That point checks out. 1, comma 0. 2, comma 1. And 3, comma 4. So each one of my points on my new parabola, just because I knew to shift it to the right by 1 unit, all worked out when we check it mathematically. So we know that this is a good rule for left and right motion. So next up, we're going to try some up or down motion. We know this, a minus on the outside, is going to be a downward shift. So I'm going to take my parent function, which existed right here, curve it through. There we go. I have my parent. I'm going to take each one of those points and shift it down by 3. So 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. And so it looks like my new function is down here. So y equals x squared minus 3. And if you're doubting yourself, or if you just straight up forget these rules, you can always check your work, or you can always just graph it from scratch. Now, I'm going to pick, because my x values haven't changed, so I'm going to test the same points. Realistically, if like the question before, you don't know the points have shifted, you just test negative 2 to 2, graph those points, and you'd notice the fact that you'd have a point way up here on the left, so I couldn't actually graph negative 3 on here. And I would stop right here. I might wanted to have included 3 after the fact. So let's plug them in. So if I plug in negative 2 squared, negative 1 squared, 0 squared, 1 squared, and 2 squared, and I subtract 3 from each one of them. Negative 2 squared is 4, minus 3 is 1. Negative 1 squared is 1, minus 3 is negative 2. 0 squared is 0, minus 3 is negative 3. 1 squared is 1 minus 3, which is negative 2. And 2 squared is 4 minus 3, which is 1. So let's check to see if these coordinates are on our new red graph. So negative 2, comma 1, that checks out. Negative 1, negative 2, that checks out. 0, negative 3 checks out. 1, negative 2 checks out. And 2, 1 checks out. All 5 of these points check out simply because we knew to just move the graph down by 3. So let's try something with a stretch or compress. Now we talked a little bit about the fact that with an absolute value, this is the slope to the right, meaning we'd go up 2 over 1. And that's kind of going to be the thing. The higher the slope, the steeper the graph gets, the more vertical that v went. That quadratic is also going to bend a little farther up. Pardon my excellent animations there. So with this 2x, what we're going to do is we're going to know the fact that our parent graph is going to be stretched. And a quick way to do this, if this is our parent, is I'm going to take, okay, so this is doubled. So each one of these y values, I'm going to double them. So I'm going to say double 0 is 0. Double 1 is 2. Double 1 is 2. Double 4 is 8. This is actually off my graph, and this is off my graph. So if I really wanted to show this, I'd actually have to squish the graph in order to show that the graph has stretched. Let's take a look at what this looks like. Curve it through. There we go. And so we notice that the graph that was wider and shorter is now getting a little taller and skinnier. It looks like somebody has quite literally pulled on the graph. And so let's test out some of these points to make sure that we can actually do that. And if I have my new y equals 2x squared, if I plug in -2, I'm going to do order of operations, so exponents first. So -2 squared is 4 times 2 is 8. Yeah, that's the graph. That's the point that's off my graph. -1 squared is 1 times 2 is 2. That checks out. 0 squared is 0 times 2 is 0. That checks out. 1 squared is 1 times 2 is 2. That checks out. 2 squared is 4 times 2 is 8, and that's my last point that's off the graph. So again, all 5 of those points check out because we realize that this was a stretch, which means the y's get multiplied times 2. I'm not going to put yx2, I'm going to put y parentheses 2. So let's try one that's not a stretch, but a compression. In fact, I want to take a pause. I'm going to pause the video. Try and see if you can figure out what we're going to do with this 1/2, and then resume the video once you're done and see how you did. Okay. So what we know is that we're going to be manipulating our parent function with our starting points right here. And so we have our parent, which is right there in blue. We know the fact that this is going to be a compression, which means our y is actually going to be multiplied by 1/2. We're going to take all those y values and squish it. So I'm going to take this 4 and I'm going to multiply it by 1/2, which is 2. The 1 is 1/2, 0, 0. This 1 is 1/2, and this 4 is 2, which is going to lead me to something that looks kind of like this. Now we notice that this blue graph, in order to make it fit, would have to be squished downward. So y equals 1/2 x squared. So let's see how good we were by checking our work. 2, -1, 0, 1, and 2. So I'm going to take 1/2 times each one of these. Squared, -1 squared, 0 squared, 1 squared, and 2 squared. We know -2 squared is 4. Half of 4 is 2. So that one checks out. -1 squared is 1 times 1/2 is 1/2. So that one checks out. 0 squared is 0. Half of 0 is 0. That checks out. 1 squared is 1. Half of 1 is 1/2. That one checks out. And then 2 squared is 4. Half of 4 is 2. And all 5 points check out. So we know that we can either do it from hand, or we can remember that multiplied outside is either going to be a stretch if it's bigger than 1, or a compression if it's smaller than 1. So this is going to be the last one that we're going to do. So pause the video real quick, give this a shot, resume it when you're done, and see how you did. Okay, let's see how it worked. So it looks like I have 2 transformations. I have a +1, which means we're going to be moving to the left, and I have a -2 on the outside, which means we're going to be moving down. So when I graph my parent function, I'm going to take each one of these points and move it left and down. So I'm going to take my point right here, move it left 1, down 2. Take this point, move it left 1, down 2. My origin, left 1, down 2. My next point, left 1, down 2. My last point, left 1, and down 2. And if I connect all these points with a nice curved parabola, we see the fact that this graph has definitely been shifted to the left and downward. So we're going to label this as y equals x plus 1 squared minus 2. Perfect. And so if we check our work, let's go ahead and double check. If I plug in negative 2, negative 1, 0, 1, and 2. If I plug in negative 2 plus 1, negative 1 plus 1, 0 plus 1, 1 plus 1, and 2 plus 1 squared all the way up, minus 2. See, negative 2 plus 1 is negative 1, squared is 1, minus 2 is negative 1. So negative 2, comma negative 1. That checks out. Negative 1 plus 1 is 0, squared is 0, minus 2 is negative 2. So negative 1, negative 2. That checks out. 0 plus 1 is 1, 1 squared is 1, minus 2 is negative 1. That checks out. 2 squared is 4, minus 2 is 2, so 1, 2. That checks out. 3 squared is 9, minus 2 is 7. I don't have a point right over here, but I bet you that would check out. The only point I haven't checked out is negative 1, negative 2, negative 3. So I'm going to check out, see what happens when I plug in negative 3. And I'm hoping to get 2. So negative 3 plus 1 is negative 2, squared is 4. 4 minus 2 is 2. Yep, they all check out. And there we go.